Thanks for inviting me. I've got 10 minutes to get over some of these ideas, and then we'll have a few minutes for questions. I'm going to be talking about the socially distant city, and I'm going to be speculating through the medium of simulation. The socially distant city probably doesn't exist as such. A version of it exists in terms of lockdown, basically. But what I will be doing is presenting a theoretical model of a hypothetical city and examining some of the key features that really relate to social distancing due to the pandemic. Let me tell you what I'm going to talk about. Very briefly, I'm going to talk about the idea of social distance. It goes back a long way. If you go back to the plagues of the past, you go back to the Great Plague in 1666, people were social distancing all the time, even though the disease, the bubonic plague, was not spread respiratory in that sense. But avoiding people is all important. And in terms of the current pandemic, working from home, avoiding crowds, avoiding public transport, these are very key issues that really relate to the situation that we face at the present time. I'm going to begin by saying a few words about that, and then constructing the hypothetical city. The hypothetical city is a city on a grid, basically. The grid can be as big as you like, in a sense, but I'll show some examples for an 11 by 11 grid with 121 locations. I'm going to lock it down in that sense. Once I've locked it down, and I'll show you how I do that, I'll enable the lockdown city to respond to artificial constraints. I'll actually let the model itself release the lockdown in that sense. And then I'll explore the space of possibilities. Once we've got a model like this, we can look at lots of different ways of thinking about what the city does. In a sense, this is really all about looking at how the city is going to spread out or become more compact under different assumptions. And then next steps, because this is very preliminary work, it's just really begun, I'm going to try and make it all more realistic, although I'll just give you an indication of that. Okay, so there are massive changes in location that have happened at movement during the need to keep people separate, social distancing, keeping away from each other by 2 meters, etc. You see that everywhere. People are working at home. They're avoiding crowded places like city centres. Public transport, certainly in the UK, has basically collapsed in a sense. It's essentially now nationalised by the government, being bailed out. And there's been an increase in car usage and indeed in active travel. So we have these polarities of increasing cars at the same time as increasing walking and the avoidance of public transport. Many of these trends are very counter to what was slowly beginning to happen prior to the pandemic, because over the last 30 years, cities have begun to concentrate a little bit. They've begun to compact. And of course, the demand for out-of-town living leading to sprawl has actually increased. And this is really a reversion to locational patterns of the mid-century. We do have some data. The Google mobility reports, basically, and the Apple mobility reports give us some very good data about occupation, taken largely from the media that those companies control. What you see here, the 2 diagrams on the left are from Apple, from the Apple mobility reports, and the 2 diagrams on the right are from Google. Basically, they're fairly similar in some sense. And what they show is over the last year, the horizontal scale is the number of years, the number of days, I should say. Over the last year, we see this enormous lockdown. This is in the UK, for the enormous lockdown in March last year, and then a gradual recovery. And if you trace the orange line, the reddish orange line, then that represents transit, basically, which is one of the best examples that we can see. There are many things you can unpack this by looking at. I should say that the diagram on the left, the first diagram on the left is the UK from Apple, and the next diagram is London from Apple, basically. So we've got UK London from Apple, UK London from Google. Okay, so that's really the context, etc. Let me begin by showing you how we begin to build a hypothetical city. Here's my 11 by 11 grid. And first of all, what we do, because we're going to explore concentration and deconcentration in this context, we actually build a kind of null hypothesis. We use the gravitational model, the inverse square law, as you can see there, and we build a model of this kind which shows you, sorry about this, I'm not getting a thing going through on my mouse. Okay, so this is the directionality of the grid, highly symmetric in this sense, as you might expect. You take a grid like this, the most accessible point is the center in that sense, and we apply our sort of null hypothesis model, the inverse distance law, to get, first of all, a pattern for origins and destinations, and then a pattern for origins, I should say, where people live, and destinations where people work. And they're both identical because this model is symmetric. This unconstrained gravity model, the null gravity model in some sense, tends to be symmetric. So that's our kind of basic landscape. The next thing we actually do is we impose a hierarchy on it. And you see what we've done artificially. We've imposed a big city center and then some edge cities around the edge, basically, and some hubs in the middle. Not very different, in fact, as an abstraction from what goes on in London. We've got about this many biggish off centres, basically, in a sense, within London. So this is our hypothetical city, and we basically build it in this sense, and we impose the hierarchy. We then work out a consistent trip distribution using a W Constraint Model, essentially, on that particular pattern. So let me just go back one. If you look at the observed origins in the middle there, and the observed destinations, which are the same, we change the destinations by imposing this hierarchy on the structure. I should say that one of the kind of key features I've discovered in using this model and playing around with it is that essentially it's very difficult to break the symmetry. The symmetry which you impose is very strong, and that really, to some extent, is one of the key findings, I suppose, from this theoretical work or this speculative work, that it is really very difficult to actually push people to the edge of things. In other words, there are so many layers of symmetry and monocentricity in this particular context that it's very difficult to conceive of a situation where that begins to disappear and everybody moves to the edge, basically. That's really, to some extent, a conclusion. What I actually do is actually show you a situation where we can break symmetry. You can see we have the origins and then the destinations where the edge cities, the centric cores are actually on the edge, basically. And you can see the directionality, the sort of vector field diagram on the right there, basically shows how symmetry is actually broken. Okay, and the model that we actually fit, of course, to this, after we built our null hypothesis, is the W Constraint Model. So we have a completely consistent city, highly hypothetical in that sense. Now we're going to lock it down. What we're actually going to do, what we do is we actually take a proportion of the people in the destinations and we move them to origins, a proportion meaning that people who work at the destinations are moved to the origins, basically. So in other words, we start with the origins on the left. We have the destinations that we've imposed and built a pattern of, a second from the left, basically. And then what we do, we take a proportion of these. We've taken a proportion that you see here, which is a proportion of these, and we move them in a sense to destinations. So in other words, you look at the two equations. The origins are a function of those who, the origins are where people live. They remain at the origins, a proportion of them, in that sense. In other words, people stay where they live in that sense. But in fact, those that, a proportion of those who are working actually move to their origins in that sense. So the second equation is essentially that. You probably have to think a little bit about it to actually get it, but it's not difficult. We're simply moving people from work to home in a sense, but there's still, of course, represented in terms of the pattern of work in that sense. Okay, enabling the to respond. What we've done once we've got a picture of a certain amount of people working from home, and we can vary that from no people working at home at all, which is the existing situation, to everybody working from home in this particular context. What we actually do is we actually let the model adjust in a sense. And what we've done here, you see that on the left, top left, we have where people are working, people are living at home in that sense, and also working at home. And on the, we have the destinations which contain people working from home, which is very different from the monocentric pattern that we imposed, basically, because we've moved people at that point. We then run our unconstrained simulation model, and we look at how people might adjust according to that model. And what actually happens is that those who are in terms of where people live are beginning to concentrate a bit, and there's a little bit of concentration in terms of where people work in that context. So essentially that's a kind of adjustment process. Okay, now we can actually begin to make this more realistic by introducing some random perturbations, and this is what we do from the data in terms of the origins and the destinations. Those are random noise added to the previous two patterns, and then we run our model and we produce a picture which is the two elements on the right, and then basically if we let this run indefinitely in this sense, then basically this is the kind of pattern we get, that the symmetry is reinforced over and over again if we run this model in that particular fashion. In other words, what we're trying to do here is find the conditions under which we break symmetry and break the monocentricity. Okay, now I'm pretty sure that I'm running out of time. So let me go very quickly and give you an idea, and I'll post this PowerPoint. Essentially what we then do is we actually build a new distribution function, a gamma function, which enables us to actually adjust the function in some sense and to rerun from our lockdown situation and let people respond according to these different curves. We argue that these different curves represent really different preferences in some sense for living near and living far in that sense. Those of you who are familiar with the gamma function will know that the two parameters control that effect. And what we then do is from this space where we have these parameters, we can actually sample different situations. And the sampling of different situations, let me go over that quickly, the space. Basically, what we effectively do, these are just 9 samples from our space of possibilities, and I'm just going to go through them in a sense to show you. Now, that's one where we have a gamma function pushing people to the edge. So we're not breaking symmetry, but we're pushing people to the edge. These are the 2 features, so on and so forth. We've got 9 of those possibilities. And the last slide, last but not least, is really where we go from here. We can obviously do all of this on a much bigger grid. That's done on a 51 by 51 grid, basically. And you can see that that gives us about 2,500 zones. And if you look at the picture on the right, that is London and the outer metropolitan area, which we've built various models of over the years. And the object of the exercise now is to begin to move to the real situation and begin to explore what I've explored hypothetically in the context of this real, with a view to actually trying to speculate and answer the question about whether or not people will move to the edge or move to the center, and how the symmetry or otherwise would be reinforced or broken in some sense by this. Thank you very much. Back to you, Rolf.
Thank you so much, Mike. This was a wonderful opening of this webinar, a great keynote that you gave us here. In particular, I like how beautifully you visualize your results. It makes it so much easier to follow. Great. We have time for one quick question that we can now have here in the plenum. If anyone wants to raise your hand or speak up with one question. If not, Mike, let me ask you one question. So you introduced the gamma function that you're using. And I was wondering, based on the theoretical consideration, why did you choose the gamma function? I mean, you could have also chosen an exponential function, another shape that you use. Why particularly?
Well, the gamma, of course, combines a power law, really, with or an inverse power law with a negative exponential in that sense. And it's arguable that in terms of social distancing, people want to keep away from things in some sense. Now, this is writ large. Our social distancing, of course, really relates to individuals on very small distances in some sense. So it's a bit like thinking of a social distance effect for the whole thing. Effectively, I think there is some evidence in cities that shows that we tend not to live on top of the place. And even if we live near, we don't live on top of in that sense. So by altering the power function element in the gamma function, we can push people away from where they work or from where they live, whichever way around we're looking at it. The two factors basically give us the ability to actually spread people around in lots of different ways. Now, I'm not suggesting that one is any better than the other. Most of the time, in terms of our models, we've used a negative exponential in that sense, or an inverse power, but not both. Although there was a proposal back in 1961 in the UK by John Tanner, who suggested that one of the problems with the inverse power law, of course, was that if you simply use that in a gravitational model, you'd have these infinite trips, as it were, or probabilities at the origin. And therefore he suggested, then the negative exponential was suggested, and equally well, there was an argument it was very difficult to fix the origin too. And in that sense, he put the two together. So he suggested it back in those days. Various people, I think, since then, a number of people since then have played around with that function as an alternative to either the inverse power or the negative exponential. It just gives us the flexibility, Rolf, to actually begin to explore. And I'd very much emphasize the fact that this is, my subtitle is speculation through simulation in that sense. So to some extent, I'm well aware that we need to get this question of the degree to which we can produce plausible or realistic kind of scenarios with hypothetical models of this kind.
Very interesting. Thank you so much, Mike. And of course, there's the option to continue the discussion with the Facebook group or via email.